Hello, today we're going to be talking about symmetry, and mathematicians give these things a name. They group symmetries together, so they call them groups. And with that, we'll see where all this goes and how it might relate to the mysticism and spirituality that we find linking mathematics to the world around us. So hold on a second while we get going here with the, and here we go. So what we're dealing with here, we have our universe over here that's in 26 real dimensions, 10 for matter, 10 for dark matter, and another 6 here that 26 real dimensions. But the thing that's in this is when we study symmetries of groups, and in particular, things that we'll see are called finite simple groups. There's a set of symmetries that don't fit into any class. They just show up out of nowhere, literally, and they're called sporadic. And surprisingly, there's 26 of those. And so all 26 of them are shown here in this figure, and we'll take that, keep that in mind. So we have 26 real dimensions and 26 sporadic simple groups. A lot of this material you'll find in a wonderful book by Mark Ronan called Symmetry and the Monster, which covers a lot of the history of how mathematicians dug into symmetries and why they believe that they now have a good handle on what it's all about. But that just means our ignorance is at a higher level, and we're going to be seeing things go from here much higher and higher. So again, here's our picture that we started with, our geometry of the universe. I called it symplectic here because, for example, all of the matter dimensions you see here for space and time get rotated by 90 degrees to create the dark matter dimensions. And then we have 6 compactified dimensions that go with matter, 6 that go with dark matter, and 6 that coordinate them. But these are each paired, so that 3 of these appear to be actually rotated by 90 degrees away from the other 3 here in each of these cases. So there's a lot of structure that's hidden here. The other thing to keep in mind is that the compartments of space are coded with what appears to be called information, and the information is constantly scanning the world around it, every compartment of space. And when it detects changes, it goes ahead and consults algorithms to say, when I detect this change, I act this way. And so the end result is that information controls everything. It controls all the matter and all the fields that are in the universe around us. So let's just cut to the chase. Here's 100 words. The mathematical study of symmetry is called group theory because it studies groups of symmetry operations. So most of these groups can be deconstructed into simpler groups, but those that can't are called atoms of symmetry. So really where we're heading here is we're going to do a periodic table of instead of in chemistry where we deal with atoms and elements that make up the matter around us, we're going to be dealing with atoms of symmetry. There's different types of symmetries that are used to build up all the other symmetries. So almost all the atoms of symmetry fit into this table. There's, in fact, 18 different types of symmetry, 18 columns in this periodic table. But surprise, surprise, there's 26 exceptions, and some of these are gigantic. One of them is called the monster, and we'll see why it's called the monster. But just as a tip-off, it involves something on the order of 10 to the 54th elements in it. So this is really a big thing here that's underlying everything. After this monster was predicted in 1973, it had shown strange connections to other parts of math, and these other areas were called moonshine because they linked the mathematics of this group theory that we're talking about here with string theory, which is a way that physicists have come up for talking about the vibrations of strings, in fact, are what controls everything. And that's what we saw in our earlier picture here. We'll just go back to it. The subquarks that make up matter here have 10 vibrating strings, and they capture energy in it that leads them to this hierarchy of subquarks. 3 subquarks make a quark, 3 quarks make a proton or a neutron. And similarly, for dark matter, we have 5 strings that vibrate, not 10 like in matter, and they vibrate and capture energy, but there's no charge associated with these. So the subquarks are the basic elements, and we end up with a atomic chemistry here for the subquarks that you'll see. So having said that, what's a group? In mathematics, a group is a set of operations. If we do A plus B plus C, and we do A plus B plus C, we get the same thing. It's associative, the group operation. There's an identity element, and that means that if we take the identity element and operate on an entity in the group, we end up with exactly what we started with. And finally, every element in the group has an inverse. If we take the element and we operate on its inverse, we come up with the identity element. So that's what we end up with, those 3 things. A lot of mathematical structures are groups that are endowed with other properties. So for example, the integers using addition form an infinite group, which is generated by a single element called 1. 1 is the identity element. And this concept of a group was elaborated for handling in a unified way many mathematical structures, such as numbers, geometric shapes, polynomials, roots, and so forth. And because the concept is so ubiquitous within and outside mathematics, some people consider it as the central organizing principle of contemporary mathematics. So let's take a look here. We said the integers form a group. So here's the integers, -3, -2, -1, 0, 1, 2, 3, going out toward -infinity, this way toward +infinity. When we use addition, we get a group. So when we take any 2 elements here, A plus B, with the group operation being addition, plus C, and then we look at A plus B plus C, we get the same thing. The 0 is the identity element. So any element plus 0, or 0 plus any element, gives you that element. And then for every integer A, there's an inverse B such that A plus B gives you 0, the identity element. Let's look at something a little trickier. Let's look at a cube. So a cube has 8 corners, and the 8 corners are made up of there's 6 faces, 6 squares that make up the faces of the cube. So if a pair of corners are joined by an edge, then each symmetry must send, if we rotate the cube, now we're looking at rotation here, must send this pair to another pair that's also joined by an edge. So that means that the cube ends up with 48 symmetries, 24 of which can be realized physically on a solid cube, and the other 24 effectively turn the cube inside out. So let's look at these 24 physical symmetries and notice that, again, there's 6 faces, any one of which could be on the bottom, for example. And then this face can be rotated into one of 4 different positions. So there's 6 times 4, or 24 right there out of the box. So each of these 24 positions can be reached by doing a single rotation. And here's how it works. Each rotation must leave the cube occupying the same space before and after. We can't change that. But without distinguishing the faces of the cube from one another by colors or numbers or other markings, we can't tell whether a rotation has been done. So each possible rotation has an axis. Think of it as a spindle that goes through the center of the cube. Now there's a lot of possibilities, 3 for the spindle. Either it goes through the center of 2 opposite faces, goes through the center of 2 opposite edges, or goes through 2 opposite corners. The cube has 6 faces, so there are 3 pairs of opposite faces. The spindle goes through the centers of 2 opposite faces with 2 possible 90-degree rotations, one going one way, one the other. This gives 6 90-degree rotations. There's also 180-degree rotation when the spindle goes through the center, 2 opposite faces. So this gives us 3 more further rotations. Okay, as cube has 12 edges, so there's 6 pairs of opposite edges. So the spindle going through the center of 2 opposite edges. The only possibility is a rotation of 180 degrees. This gives us 6 rotations, 1 for each pair of opposite edges. And then finally, the cube has 8 corners, so there's 4 pairs of opposite corners. The spindle going through 2 opposite corners are 2 possible rotations, both of 120 degrees, one going one way, one the other. So there's 8 120-degree rotations, 2 for each of the possible corners. So there's 6. We got 6 up here, plus 3, plus 6 from this one, plus 8. And then we have the rotation by 0. This takes us to 24, and these are all the rotation group elements of the cube. Now let's look at something a little different, the symmetry group. The symmetry group is a set of n symbols. Now this forms a group when we look at permutations of these symbols. So let's just think of them as 1, 2, 3, 4 on up to n. So you just think of it that way. And we can permute these things. So we start off with 1, 2, 3 on up to n, and we can switch 1 and 2. We can switch 1 and 3. And so then how many of these things do we have that'll take us back to where we started from? Well, since there's n factorial possible permutations in a set of m symbols, then the number of elements in the symmetric group is n factorial. That's the thing to keep in mind. So let's take a look at it. Let's start off with a point. We'll think about this geometrically. So if there's one point, then it's just sitting there, and we'll think of it as the number 1. It doesn't go anywhere. It doesn't do anything. So there's really only one element in this symmetry group with one element in it. Now let's go to the symmetry group with 2 permutations. Think of this as a line that has 2 endpoints. So there's a 1 at one end and a 2 at the other. And we can switch them and so forth. So the number of elements in this is 2. I can take it 1 to 2 and 2 to 1. So I have 2 elements in this, or 2 times the number that I had in 1, 2 copies of the symmetry group S1. Now I go to 3. I have an equilateral triangle here. Think of it as the corners of the triangle labeled 1, 2, 3. This means that I have 6 possible rotations that I can deal with here due to the permutations that are going on here, which is 3 times the number that I had for 2, or 3 copies of the symmetry group 2. I go to a square, I end up with 4 copies of the previous one. I go to a pentagon, again, 5 points here. I end up with 5 copies of this. Now when I go to a hexagon, something crazy happens. I end up with 12. That's 6 copies of S5. And an example of something that becomes a split or a sporadic group. So these things do occur in abstract algebra. A finite group is a group whose underlying set is finite. Finite groups often arise when considering symmetry, when those objects admit just a finite number of structure-preserving transformations. So structure-preserving would be translations, rotations. I could expand everything. I could shrink everything. So the structure is always preserved by all of the actions, all of the transformations I just described. And this leads to cyclic groups and permutation groups as examples of these finite groups. The key thing here is that it's only been until 2004 that mathematicians were convinced that they classified all of these finite simple groups. And that meant that there were no non-trivial subgroups here that were hidden, that they had missed anywhere. everything had been classified. It took 150 years and literally thousands of mathematicians to do this. So that takes us to what is a sporadic finite simple group. So the finite simple groups have been classified into the 18 simple group families. These are the things I talked about as examples of translations, rotations, scaling up, scaling down, and so forth. And there's just an infinite number of those. I can translate an infinite number of ways. I can rotate an infinite number of ways, and so forth. So the finite groups are all classified into these 18 elements here, 18, if you will, columns in this periodic table. However, 26 of them don't belong to any of these 18 families. And the 26 don't seem to have much in common with each other. So instead of calling them just miscellaneous, mathematicians call them sporadic. So what in the world is the history of the sporadic group? Well, in the mid to late 19th century, the French mathematician Émile Mathieu created 5 exceptional groups of permutations, the largest of which is called today M24 in honor of Mathieu. But they didn't fit into any sort of later periodic table, and everyone was puzzled about these 5 exceptions. And it took like 100 years. It shows you how challenging this is, until a Croatian mathematician, Janko, found a new one, and he published this in 1966. Now, since there's one, mathematicians immediately started to jump on this, say, are there more than one? And this led to all kinds of things being done with mathematics being invented along the way. There were some that resulted in interesting permutations, some that were geometric, some that looked at what we call cross sections here. And these things get to be very technical, but the construction of the sporadic group was usually tricky, usually involving computer techniques. And the monster, the largest of the sporadic groups, was predicted by this cross-section method, but its size and complicated structure rendered the computer methods impractical for a while. It had to be constructed by hand. So there's 2 main threads that led to this monster group. One was the Leech lattice that we'll talk about, and the other was the Conway groups, the Leech lattice and the Conway groups. And then there was the baby monster that was related to this. So let's look at those. The Leech lattice, that was a 24-dimensional lattice created in the 1960s by John Leech, and his design discovered in the used a design discovered in the 1930s by Ernst Witt, who created it in order to construct the largest Mathieu group, N24. So Leech used it to obtain a remarkable way of packing 24-dimensional spheres, which is still used today in communications for coding of sending signals over noisy channels. The symmetry of this lattice was investigated in detail by John Conway, an English mathematician who was at Princeton for many years and is no longer with us. And so the end result of this was there are now 3 new sporadic groups known as Conway groups due to Conway, based on staring at this Leech lattice. The monster group came about with this German mathematician, Bernd Fischer. He created 3 large, remarkable sporadic groups that were related to, but were far larger than the 3 largest Mathieu groups. And then he found a huge one, later named the baby monster. And the baby monster led to the prediction of the monster that was an even larger one than the baby monster. And having worked on this for a while, they determined that the monster could operate in 196,883 dimensions, which happens to be 47 times 59 times 71. 3 prime numbers, 47, 59, and 71 dimensions at a minimum. And this was the number that was calculated by an English mathematician at Cambridge. So having worked on this, you ended up having a 196,883 dimensional space, and the elements in this space are on the order of 8 times 10 to the 53rd, which is a big, big number. So this led to other mathematicians working on this, and so it went. So let's look at this more. The 196,884 came about through a remarkable coincidence. 1978, the English mathematician John Mackay noticed that it was the first non-trivial dimension of a space that the monster operates in, but it's also the first non-trivial coefficient of something called the J function, which appears in number theory. And what does number theory have to do with group theory, and in particular with this number 196,884, which is number theory deals with the study of whole numbers and is a very, very different branch of mathematics, but maybe they're not very different. Maybe they're linked in some way. So Mackay sent this coincidence off to a colleague at Cambridge, John Thomson. Thomson was working on this, and he explained what he'd heard to John Conway. Conway dug into this, and looking at the monster's character table, which we won't get into here, he and Simon Norton proved there was a definite connection between the monster and the J function, and they dubbed the whole thing moonshine, referring to it as a great mystery as yet barely understood. So there's some incredible linkage number theory with this J function theory published called Monstrous Moonshine. And there was a space in infinitely many dimensions that exhibits connections between the monster, the J function, and other J functions. And these ideas were picked up by other mathematicians, and they came up with something called the Moonshine module, which turned out to be connected to the mathematical physics of string theory. String theory is the theory we mentioned before, dealing with vibrating strings for matter and for dark matter. So the Conway-Norton conjectures from the Moonshine module were also proved by the English mathematician Richard Borchers, who also gave another approach to the monster, citing with a lattice in 26-dimensional space-time, which is what we think is our universe, 26 dimensions. All of these finite groups really become the atom in a periodic table of symmetries, named after the Norwegian mathematician Sophus Lie, or they're one of these 26 sporadic groups. So there's 18 of this finite simple groups, and this classification started off really to get some steam in the early 1960s, and then kept on going. And there's now a whole bunch of research papers that in excess add up to over 10,000 printed pages. And there's a complete revision of this proof that had come out in 2004 that is ongoing and will simplify all of these things, apparently. So mathematicians are heavily engaged in this. Here's this periodic table of finite simple groups, has 18 columns here. Down at the bottom, we have 13 times 2 rows of 13 sporadic groups that don't fit in anywhere up here. So the thing that was proved here was that every finite simple group is isomorphic. It's one-to-one. It matches identically, and there's nothing that's missing into one of the following groups. There's a member of one of three infinite classes: the cyclic groups of prime order, the alternating groups of degree at least 5, and the groups of Lie type. These are the ones that I mentioned before, were translations, rotations, scaling up, scaling down, simple groups with infinite classes, and 26 sporadic groups. The examples we gave before of the finite simple groups are these. There's others. For the sporadic finite simple groups, there's a whole series. All of them are named here, so you can see. And the history of this is that in the mid to late 19th century, Matthew did this, Janko then did his thing, and then the rest followed. We gave you an example before of this quirk that leads to these sporadic groups. And so it goes. There's nothing to say about it other than they're just quirks. They don't lead to anything more. They're a dead end. The monster group is this size, which works out to be 8. If you look at this thing here, it's 8 times 10 to the 53rd. If you look at all these numbers here, and this ended up with all kinds of connections to other things here. There's also a connection here to Golay coding. This is used in information theory and sending coding signals to go over noisy channels. The class of codes that Golay originated in 24 dimensions. There's a second number, which is the number of spaces of 24 by 24 symmetric matrices. And then there's a third number, which comes out of this Leach lattice. So the character table of this monster, something we're not going to go into, is a square array of numbers, rather like a big Sudoku puzzle, 194 rows and columns. And the first column generates an important sequence of numbers in number theory, coefficients of the J function, and the other columns can be used in a similar way. And we think that this might lead to all kinds of other connections of mathematical physics and string theory to this area of mathematics. Here's an example of a mystery associated with the monster. The 194 columns of the character table span a space of 163 dimensions. The number 163 in number theory is well known because the square root of this, minus 163, leads to an extension of the rational numbers having a unique factorization. This is the largest integer having this property. So we touched on before different ways that these things could be related. The numbers 4, 6, 24, 18, you name it. And with that, we'll close it out. Have a good day.